Hi, so today I want to talk about how to calculate moving averages in a really fast way. Why do we need to calculate moving averages in a fast way? Well, imagine sometimes you have a trading algorithm and you get a trading signal in which is based on a moving average, and you want to execute it in a really fast, speedy way. Now, how do we calculate moving averages normally? We just take the past n data points, so for example 100 last 100 minutes, and we sum them up, and then we divide them by 100. That's a normal moving average. Now, in order to do this, we have to sum up 100 numbers, and in most cases that's actually a pretty fast process. However, sometimes we're really looking for fast execution and we want to go perhaps into the microsecond region where we really want to shave off this just tiny little bit of execution time that stops us from being really far in the queue and going really up there. And so we probably need to find something that does our calculations a lot faster. And today I'm going to show you how to do this, moving from a regular moving average to a exponential moving average. Now, exponential moving averages can be calculated just as regular moving averages. So for example, we could use TA-Lib to do this. Now, in order to do that, let's first get some market data. And I just used the simple S&P 500 index ETF SPY. And as you can see here, I've imported a few packages: TA-Lib, NumPy, yfinance, Pandas, datetime, and matplotlib. So I go yf to download. Download SPY, and that just downloads the S&P 500 index, and actually we just want the adjusted close prices. Okay, so now if we wanted to calculate an exponential moving average, we could just, for example, do this: TA-Lib EMA TA-Lib equals TA-Lib dot EMA exponential moving average. We go SPY, and then we have to put a lookback window. Let's just do 100, and so this is calculated at pretty fast. Now, this is actually calculating the whole window at once, but what happens in a normal trading algorithm, we have a time step, and every time step we do it again and again. And let's just say we have a really fast algorithm that calculates a new time step every second. Now, in our case here, I'm working just for the ease with daily data, so we're not actually doing it every second, but what we can do is we can actually put a normal moving average in a loop and then calculate it. So let's just do this. So for example, we could do something for I in range length SPY, and then let's just go and not use the whole we could use the whole SPY, and then we can do something like moving average equals mp.me. Let's just go SPY.ilog, and then we go I minus, and then we call this the lookback all the way to I dot mean. So this is just the average that we calculated in that moment, and then we could do something like MAS, our MAs dot append MA, and then what we can do here is MAS equals nothing. And so this is basically running through different time steps and recalculating our moving average 100 period backwards. In this case we have days, but you could see that if we had 1 second data, which we can't get from yfinance, we could do the same, and we can just run this. Of course we need to define the lookback, so let's just do this: lookback 100, and here we go, we run it through and it takes a little while. So what we could do, for example, is we could clock the time. So we could say start datetime.now, and then we print the runtime print, and then we go datetime.now minus start. Now there's other ways to do it, of course, I know, but this is just a very straightforward one. And name datetime is not defined. Data time, sorry, still got this. So it runs, and it takes about 1 second to run through the whole data set with all our calculations. And you know, as you know, the S&P is about 200 starts at about 1992. So let's just quickly plot this out just to see what this looks like. So the first thing we do is we just go spy.plot. So this is plotting the S&P, and then one thing we can do is we can go plt.plot, and then we do spy.index. This just gives us our index, and then we do MAS, and that just plots our 100-day moving averages. In this case, as you can see, they overlap quite a bit because we do such a long time range. If we made our look back a bit larger, say 1,000, then of course this would look quite different, like you can see here. But let's just leave it at 100 at the moment. So let's rerun this again. Now, one thing we can do is we can actually go, okay, what happens if what we're calculating here is a little bit on the slow side? You can see it just runs through step by step, and it calculates. It always takes the 100 data points, takes the average, and then spits out the moving average. But this could indeed be quite slow for some high frequency applications that we use. And another way to do this is to actually use an exponential moving average. And the interesting thing with the exponential moving average is that when we use it, we can actually run it, and instead of always having to calculate a vector of 100 data points and sum it up, we can actually just go and always just update the last EMA value. So the calculations will naturally be quite a lot faster. And how do we do this? It's fairly straightforward. So one of the things we could do, for example, we need to start with a starting value. So we could, for example, do EMA equals spy.ilog, and we just go with the zeroth value, and then also we want to record our EMAs. And then once we have done this, what we can do is we can calculate the EMA. So we can go EMA equals, and then what we need to do is we need to calculate the current price, which is basically spy.ilog of I times a constant, let's call it K, plus. And then what we need to do is we need to calculate the previous EMA. So I call this EMA. So as you can see here, this is just the old EMA, and then this is the updated EMA. And we need to multiply this times 1 minus K. Now, how should we determine K? What I'll do is right now, I'll just set a value, and I set it to 0.02. Okay, so now we have this, and we can of course do the same emas.append EMA and run this again. And as you can see, it's actually still running at around 1.5 seconds. And what we can do here as well is we can go MAs and EMAs, and then you can see they're all overlap, so they're actually in some sense all quite similar. We go into a little bit more detail how we can, for example, if we just wanted a simple moving average, adapt it a bit closer to the EMA. Okay, so now you saw we had about 1.3 seconds before. Now we have 1.5. Now what happens if we don't use the moving average? So we comment that out and we see what the runtime is. And as you can see here, it's actually 72 milliseconds versus 1.3 or 1.5 seconds. So let's just run the other one again. And it takes significantly longer. So it takes 1.34 seconds. So if we just do a calculation, 1.34 divided by 0.075. So we can see that if we run the normal moving average, calculating the whole vector, in fact, it takes about 18 times longer. And that's a significant difference, especially if we want to get a really fast turnover from getting in the signal and submitting our trades. So that's a really, really big advantage. Now the question is, perhaps we tested our system on a simple moving average or whatever. How would this help us to get the set? So is the exponential moving average and the simple moving average similar? So let's have a look at this. Okay, in order to do this, let's make our plot a bit bigger first so we can see a little bit more. And what we also want to do is get this running again so we can see what's going on. And then we go plt.figure fix size equals 1510. And here we got our bigger figure, so we can already see a little bit more what's going on. And then all we want to do is perhaps just use a few values. For example, we could go -n into the end, and we do the same for everything else here, just so we can get a little bit less of the figure, and we specify n, and let's just say n equals 1000. Let's see what that does. And so we can already see here, this gives us a much better and clearer view. And you can see one of them, of those figures, is the moving average. Another one is our exponential moving average. So let's just go and label these figures. Label, and here we have our SMA, simple moving average, and then in this case we have our exponential moving average, EMA, and here we go label equals SPY plt.legend, gives us our moving averages. And here we can see the green one is the exponential moving average. You can see it responds faster to those drop downs, and the simple moving average responds a bit slower. And all in the other cases where the shocks are not so great, we can actually see that the moving averages are overlapping quite significantly. Now, is this good or bad? We don't know, but for example, what we can do is we can just change k. So at the moment it's 0.02. What happens if we just set it to, for example, 0.1? And so we run this again. And now you can see that the exponential moving average is a lot closer to a much shorter lookback window of the simple moving average. So maybe that corresponds much more to a lookback window, for example, of 10 than what we had before. So the exponential moving average is much more different from the underlying simple moving average. Okay, so we've got 0.01. Let's go back to the original value, 0.02. What happens if we go much smaller than that, 0.005? And what we would expect is that this corresponds to a much longer lookback window. and this is here, as you can see. So the question is, what is the optimum lookback window that we can see? And of course, there must be some sort of a relationship, and we could go into the mathematics of it, or we could perhaps just find some kind of ballpark figure. So let's just do this. And one way to do this is we can just calculate the differences between the moving averages and the exponential moving averages. And then we can, for example, just say, well, which of the values is closest between the two, and that is the value we could pick, and then we can see if we find some sort of relationship between those values. A simple way to do this is just to simply take our moving average and our exponential moving average, calculate the difference, and then see at which lookback period the difference is minimal. And then we can say, well, what is the best lookback period, how does the best lookback period compare with the factor that we use for our exponential moving average, and maybe we can infer some sort of ballpark figure that gives us a reasonable estimate of where the two moving averages are the most similar. So in order to do this, let's just go and write a loop for, and let's just go from a lookback period of 20 to 200. And then what we need to do is we need to calculate first of all the moving average, and what we can do is we go spy dot rolling, and the rolling window is our I dot mean. And then what do you remember at the end here, we specified a specific window, but we don't want to do this now. We had the 700 window, but let's just do the whole thing. And what we need to do is we need to subtract this, and so from the moving average. So what we need to do is we need to put our exponential moving average into an array, so we can subtract the two because it was a list before. And then what we do is we sum them up, go mp dot, and we use an NaN sum. And one of the things with NaN or with rolling moving averages in Pandas is that it gives us NaNs right from the beginning. And so what we want to do is perhaps start at a higher value, and just to be safe, we would start perhaps at 500. So we do this here as well, dot ilog 500. I put it at the end here because first we want to calculate the moving average of all the values and then chop off the first 500. If we chop the first 500 off and then calculate the rolling mean again, we will then have again NaNs in front, and this is really not what we want. Alright, so we've got the difference here now, the sum of the difference, just to make sure that our brackets are okay. And then what we could do is, actually this is let's just call this MA diff. So what we can do is we can print I and MA diff, and then we see which one is our best values. So you can see here it actually decreases, or we start with 20, and then we can see the value decreases. Here gets lower and lower, and we can see that actually at 200 it's not enough, we have to go further. So let's just go with 400 and see if we find a minimum here. Okay, so we go further, and then we can see here there is actually a minimum at 374. So 374, now remember our K was 0.005, so let's just remember that we're actually close to 400 in this 374. Okay, so what happens if we change that value? For example, 0.01. Let's rerun all this again, and we can see for 0.01 our value is 193. That's actually close to 200. So we doubled our value of k from 0.005 to 0.01, and we went from 400, or just under 400, to just under 200. That's great. That's something interesting. Now what happens is if we double it again, so maybe what we could expect is to be just under 100, hopefully. And what do we see here? As you can see, it's actually 98, so that's even closer to 100. So we can see that there is some sort of trend here. Now let's do one more. Let's do 0.04. And so if we get close to 50 now, we can say, okay, we've got something here. And as you can see, this is actually 49. All right, so just by this simple calculation, what one can we do? We can conclude that let's just say we had 0.02, and then our period was close, or our closest period was close to 100. So if we say, well, we have 0.02 divided by 2, it's 0.01, and then 1 over that is 100. That's our period. So if we have 0.04 divided by 2, 0.02, and then inverted, that gives us 50, which is close to the period we had. So our k is actually quite similar to, or we can infer, at least to some extent, from our k, the closest period for our simple moving average. So there you have it. We can now build an exponential moving average, which is, at least to some extent, similar to our simple moving average, which we may have used in our previous calculations. And we have an exponential moving average, which is in fact faster responding than our simple moving average, which can also be helpful. And on top of that, which is probably one of the biggest benefits of our exponential moving average, we can calculate it in a much faster way than our simple moving average. So if we use a trading algorithm, at least in Python, we get a speed up by about 18 times, which is fairly significant. And if we have algorithms that really work with speed, and we have to do quite a few of those calculations, then this speed up really helps us to make our algorithm a lot more performant, given that everything else, of course, also is tuned to high performance. So thanks for watching this video. If you have any comments or anything interesting to say, please leave it in the boxes below. Also check out our other videos, and I hope to see you in the next one.